Very much. What I'd like to talk about is essentially Fano resonances in Photoassociation spectroscopy, and what we have been doing is some high-resolution Photoassociation spectroscopy. What I'll be telling you about is mostly spectroscopy of what's essentially the ground state, if you will, or the lowest triplet state of the Na2 dimer potential. And in doing so, what I'd like to do is also give a little bit of a different point of view of photoassociation than perhaps you've typically heard, as we're going to be talking about Fano resonances, which in this context is often pronounced Feshbach. But it's all the same mathematics, and we know this from yesterday that these are all really the same process in slightly different picture. So I'll try and give you a couple of different little pictures of what's going on in that. So before I actually get to that, let me tell you who did things. The Feshbach resonance or Fano resonance type thing was former postdoc Frederick Fatemi and collaborator from Williams College, Kevin Jones. Frederick's at the Naval Research Laboratory now. Myself, and then the spectroscopy, we were joined by present postdocs Luis de Araujo and Jonathan Weinstein, former postdoc Steve Gensimer, who's at Bates College now, and in a lot of this we have tremendous help from Ida Tiesinger, who has done some theoretical work for us, and this is at NIST in Gaithersburg. And what are we doing? Well, we have a magneto-optical trap with atoms, sodium atoms at about 0.5 millikelvin, and we allow them to collide. And they collide as free atoms along this ground state potential. And consequently, because they're free atoms and they're not actually a molecule at that point, we don't have to obey any kinds of rules as far as molecular selection rules in this photoassociation transition. So we put in a laser here that allows us that if it's tuned to a bound state in the excited state potential, it allows us to go from colliding free atoms to a bound, rotating, vibrating state of the excited molecule. Then to do our spectroscopy, what we like to do, what we want to do is poke in another laser and then look for bound states in the ground triplet state potential. You can try to photoassociate, which dumps atoms out of your trap, makes some trap loss, and then try and perturb the trap loss and have a little less trap loss here. But you know, we have any number of ways of losing atoms from our trap, and so this is not always the most positive signal. So what we do is we put in an extra ionization laser here, and we try to have a nice positive ionization signal that we can disturb by putting in the second laser down here. And so that's the way we're going to do the spectroscopy. We're not the only ones that do this. There's very similar work in lithium, potassium, rubidium, cesium, even mixed isotopes in lithium and things like that. So it's not unique in any way. What do we actually see? Well, a way to see where this comes from is if we put in our ionization laser and fix it from some bound state in the excited state potential up to some doubly excited auto-ionizing state. That gives us good molecular selection rules because it's between two good molecular states. And then we can scan our photoassociation laser across this resonance, and what you see is this blue line here. So we have a nice big peak, gives us a good signal to work with. Then if we want to see what happens when we disturb it, if we put a second laser on connecting this excited state to a bound ground state and then scan this laser across that resonance, you see this nice Otler-Town splitting of the line. So this is just simply if you take and couple this ground and excited state with a laser, you look in addressed basis, you have the excited state and the ground state with n photons, where the excited state with n photons and the ground state with n+1 photons and so on. You have this manifold of dress states. And so what you're really looking at is this splitting due to this dressing. If you scan this one, you see this nice splitting. But if you fix this one on that peak and then scan this one, you will see a nice big dip like that when the time comes that you pass through the ground state. And so that's, in fact, what we see. So this is our kind of baseline ionization signal here. And as we scan this along, we get a nice dip in that ionization signal. And that shows up right where we have a bound state in the ground state potential. Or in this case, lowest triplet state potential, if you don't want to call it a ground state. That laser also can cause some photoassociation, but we see these nice bound states. And kind of a double check on this. This doesn't actually, as far as I'm concerned, this doesn't make any ground state molecules. It's very difficult. What you're doing is you're photoassociating and ionizing, and then you're frustrating the photoassociation here by splitting that excited state. And so you don't really make molecules that way. But if you split these two steps, you photoassociate to some step that can spontaneously emit and populate these ground states, then we can ionize out of there. Since this is all done with CW lasers, we have very high resolution, and we can look at these things. And so sure enough, we can see some photoassociation peaks, but also these peaks where we're ionizing ground state molecules that we're forming. And so this gives us a way to go on further and actually make some ground state molecules and do some experiments with those. But I won't be talking about that today. So when you do this, if you do photoassociation, you're used to kind of weird line shapes. So this thin line here on the inside is essentially assuming what corresponds to 10 megahertz, or about 500 microkelvin of temperature, but no line width. So it's kind of a weird asymmetric line shape due to the energies in the collision. And the resonance is here on the blue edge of this line. If you give it some natural line width, you end up with this darker curve. And if you try and put a Lorentzian through it, you get the kind of dashed curve in the middle there. But all I'm trying to show with this is that if you look at something like the peak of this line, you've missed the actual resonance position by something on the order of kT for the sample that you're working with. If you go and do two-photon or two-color photoassociation, John Bone and Paul Julian worked out some two-photon or two-color line shapes for this. And you can get these nice dips that I was showing you. But beware a little bit. This nice dip is found by not photoassociating to that resonance. This is photoassociating to that peak, which is about, in this case, about 8 megahertz off the resonance. And so just locating these dips, you have to be careful. You want to know what the difference frequency between the lasers is, not what this energy separation is minus that, or you know, you have to be careful what numbers you're subtracting here. Because if you go off, and for this case, what I've done is I've tuned about halfway down the red side of this line, and you get these weird dispersive line shapes. And again, it's all explained in there, but it's kind of weird. You start letting your lasers drift a little bit, and you see these weird line shapes. And all right, you can retune your lasers and get them back to the symmetric ones, but sometimes that doesn't work. You end up playing around with these things, and so you set up your photoassociation and ionization laser, and you're getting that in there, and well, you put in your other laser that's supposed to do this, and it doesn't always behave quite the way you want, and sometimes it kind of rolls in there in the wrong place, and it does something that looks more like that. And, you know, this isn't such a bad thing because, you know, you didn't really expect it to go only where you wanted it. But this gives you a very weird dispersive line shape that when we first saw it, we were confused because we hadn't been thinking about looking at this through, say, Fano colored glasses. And so this was identified as a Feshbach resonance. And in fact, all of photoassociation is nothing more than optical Feshbach resonances, continually every time you do it. So Feshbach resonances, as we all know, is that there's some closed channel potential that has a bound state in it, and you send in your scattering particles, and when their incident energy is resonant with the bound state energy of this level in this excited potential or closed potential, then you get some resonant coupling into there, and it essentially bounces around in here and feeds back out and changes the phase of the scattering wave function. And so this is essentially how you change your scattering length, is move this potential around. And what we're used to seeing in cold atoms is this being a ground state potential, and we move it around by putting on a strong magnetic field and kind of bring these things into resonance with more or less zero energy collision energies in the system. So if you want to look at photoassociation as an optical Feshbach resonance, what we have now is essentially zero energy atoms colliding. We introduce a laser that, if we tune this correctly, we've connected the atoms to a bound state potential, an excited state, and this bound potential up here. And if we look at that in a dressed atom picture, again, here's the excited potential with n photons. Here's the excited potential dressed with n-1 photons. And as we change the detuning of this laser from resonance, essentially, we can move this bound state through zero energy, and it looks like an optical Feshbach resonance. And this was first discussed in this paper in '96 by Fedotchev and company, and expanded upon by Phone and Julian. And so this is what we see. What you're all familiar with now is these dispersive line shapes, very, very sharp dispersive feature, and they always have this same symmetry as we tune the laser in one direction, because essentially what we're doing is we're taking that excited potential and pulling more bound states down into the ground state. And so every time it does that, if you want to think of this, if this was monitoring a S-wave scattering wave function, you're essentially sending the scattering length through plus and minus infinity and creating one more bound state in that potential. So this was published here, and there are a number of other experiments that are in some sense similar but don't see quite this shape. Dan Heinsen's group has looked at what effect a magnetic Feshbach resonance has on photoassociation, or conversely, using photoassociation to look at a magnetic Feshbach resonance's effects. The problem is they don't have essentially a baseline ionization signal that they can work from, and so it's very hard to see a dispersive line shape if you can only go down to zero, or down to your baseline. So that it looks a little bit different there, but the context is pretty closely the same. What I didn't point out here is the upper trace is just photoassociation trap loss spectrum. This is more what we usually see. And every place that we see, say, trap loss, that we've gone through a photoassociation, we see a nice dispersive signal. And in fact, it's substantially easier to see some of these sometimes than it is to see the trap loss here. So even though we don't have very much trap loss, as long as we can couple to those states, we can see the optical Feshbach resonance. One way to look at this is that, again, we're altering the wave function with photoassociation. So think of what we've done as we set up a photoassociation laser and an ionization laser. And again, this kind of just defines what we're able to look at for that. We've got a good bound-bound selection rule here that'll select what we're looking at, what wave function we can detect in the incoming channel. And this is an optical Feshbach resonance, as I just said, but we're going to ignore that, and we're going to just say these lasers are weak and they're fixed, and all they're going to do is provide us with a monitor of essentially the overlap of this excited state wave function with this ground state scattering wave function. And so it's really just sampling what the scattering wave function looks like at the outer turning point of this excited state wave function. And so then we're going to turn on a second laser, and we're going to call that one an optical Feshbach resonance. And what that does is it allows you to couple some of this incoming flux to this second excited state. It bounces around in here a little bit, leaks back out, and produces a very different phase on your scattering wave function. And so what you've done is now with this monitor system that you set up here, you can now see the size of the scattering wave function change, and you can pull nodes through there and change the size of this substantially. And so you can make your photoassociation ionization signal go very high and get suppressed and things like that. So that's kind of the picture that we have for this. Alternatively, you can just call this interfering paths to ionization. You have the direct path that we set up as our monitor, where you photoassociate to the intermediate excited state and then to the doubly excited state and ionize. Or we can go in on this second laser that we have, excite to this other excited state here. We have one photon driving us up, another photon driving us down, and then we do the same two-step ionization. So there's two paths leading us to ions, and they interfere, and we can make this interference be constructive or destructive. It's Euler-Fano resonances all over again, and the dispersive type line shapes that I've been showing you. So what we've got here is our collision continuum coupled to a bound state with a laser. We couple it to another bound state with a laser as well, and we monitor some percentage of the population that lands in this state by ionizing it. So in general, the more general picture of this would include a bound-bound coupling as well, but that's not present in our particular picture. And if we want to be theorists for a day, we go take the formulas that are kind of standard or what appeared in the original Fedotchev paper, and we normalize the incoming flux and include spontaneous emission out of this state here. And so we've got stimulated processes here. We've got a little spontaneous emission out of there. We've got a coupling to this other state. And you can find your wave function from that and derive what the signal line shape should look like. And it's, again, a familiar thing that's essentially a baseline plus a Lorentzian plus a dispersion function. And I'll show you some fits. But before I do that, just to, again, we're theorists for a day and can do that. But in preparation for this, I thought that I'd look. There was a book. We all know that Ugo Fano spent some time at NIST before it was called NIST at NBS. And there's a book on kind of the history called A Unique Institution, the National Bureau of Standards, 1950 to 1969. It contains a nice picture of a distinguished young Ugo Fano, and had a little quote from there that in 1946, an event of great significance to the whole Bureau occurred. A pure theoretical physicist, Ugo Fano, a former student of Enrico Fermi, was hired. Goes on to say that as near as can be determined, this was the first time in its history that the Bureau had hired a pure theorist. Managed to go for 45 years without a pure theorist. And to show you what state things have gotten to now, this meeting, there are 5 of us from NIST. I'm the only experimentalist here. So. Well, of course, yes. There is. If we allow, Charles has apparently turned some bolts on a beamline at SURF, so perhaps Charles not pure anymore either. But so anyway, these are the line shapes being fit to our experiment. What I've plotted on the bottom is just a photoassociation line, and so this is for the same line that we're looking at. And so this is the rather asymmetric photoassociation line shape that we have. And this tells us where, as we tune the laser, we'll actually see trap loss. So then if we look at the optical Feshbach signal, you can see as we turn up the laser power, we can affect the signal substantially. And if you want to think of this, again, as changing the scattering length by turning on this optical Feshbach resonance, there are places that you can go where you can still make some substantial modification of the scattering length, and you have very little trap loss. So you have an extra knob here in some sense that you don't have with a magnetic Feshbach resonance. You have both an intensity and a detuning that you can play with, and you can do a few different games with that. I kind of qualify when I say things about if this is a scattering length that we're looking at, because it doesn't have to be. And what we're doing, again, is our experiments are done in a magneto-optical trap, and we can set up our monitor system here to monitor different partial waves in the collision. So if we choose an intermediate state here for this ionization monitor to be, say, an odd rotational state of the 0G minus potentials or an even rotational state of 0U plus states, those couple to only the odd incoming partial waves. And so for us, in this case, it's limited essentially to P waves. But if we choose even rotational states of the 0G minus or odd states of the 0U plus symmetry states in here as our monitor, then we can only detect from the even partial waves. And again, we do have a good molecular selection rule on this step, so that allows us to do this selection of the partial waves. And when we do that, again, we see rather different things. This is just moving the detection by a very small amount from a j equal 1 rotational state to a j equal 2 rotational state of the 0G minus. And you can see that we very clearly pick up different rotational states. This is probably j equals 0 and 2 of the incoming, or the 0 and 2 of the excited state that we're photoassociating to, and this is 1 and 3 or something like that. So just to kind of go over what we have with an optical Feshbach resonance and using that on manipulating scattering lengths, we do have intensity and detuning as parameters, and so we have some advantages. We can rapidly scan these things. We don't require scanning through the resonance to detect at or to move to a particular detuning the way you have to actually pull through with a magnetic field. We can focus our laser to a rather small spot and address just, say, half of a condensate if you wanted to. Again, as I mentioned before, we can try working away from the resonance a bit and avoid losses, which is always a big problem when you want to use a condensate. But then there's a big kind of glitch in the whole mess here. I've showed you nice dispersive signals and very obvious things in what we've done in a magneto-optical trap, but there's something called the Wigner threshold law that says that if we're going to go and do this in a Bose condensate, which is going to be 4 or 5 orders of magnitude lower in temperature than our magneto-optical trap, we're going to lose essentially the Frank-Condon factor is going to go down by root E. So we're going to lose 2 or 3 orders of magnitude in overlap, which means that we have to make up for that in laser power. And so if we really want to manipulate the scattering length with an optical Feshbach resonance, we're going to have to really hit it hard with laser power, and then you have to worry about what kind of damage you're going to do to your atoms by things like 3-photon ionization and things like that. It's maybe possible to get around this using essentially Raman optical Feshbach resonances, but I think it's actually going to be substantially difficult to use this. So the last bit here, I'll just tell you a bit about the spectroscopy that we've been doing in the lowest triplet state of sodium-2. So again, it's not very deep. It's about 160 wave numbers deep. We can get there by photoassociation going through these excited triplet states. And the way we do that, it turns out we have some very valuable theoretical input that allows us to pick and choose just exactly what quantum numbers we want to hit. So we use an intermediate state that Ida Tiesinger has done some detailed calculations on for us. And so it's not, he doesn't have the vibrational defect exactly on, but basically this is the experimental trace across the V equals 66 of the triplet sigma state that we use. And the theoretical spectrum for V equals 66 or 65 that looks essentially the same, except that there's a slightly different rotational constant for them. At any rate, we can go and look at the theoretical things, and we can look at the experiment as well, but we don't have a table of numbers that come with the experiment, whereas with the theory, Ida provides us with a nice table that tells us what all the quantum numbers are that are associated with these individual peaks here. And so we can photoassociate to something that we know the quantum numbers on very well, and then start looking at photoassociation resonances in this two-color photoassociation. So these are the dips that I showed you before. They're essentially, it's V equal 15, S wave, or J equals 0 states, lowest rotational states in V equal 15. They're bound, well, this one is truly bound by about 300 megahertz, and these two are quasi-bound states at higher asymptotes of 1 plus 1 and 2 plus 2 collisions of the sodium atoms. Then if we go down to V equal 14, 13, 12, we have for each of these scans across the rotational quantum number 0 and 2 coupling states, rotational quantum number 1 and 1 and 3 in some of these. And so we can see vibrational states that go down right now to V equal 8. We see generally rotational states 0, 1, 2, and 3 for all of these. If you look at this, no, it's not that our laser was having some jittery problems. This is actually structure on that, which I'll show you in a moment. So we're able to do some pretty extensive spectroscopy of that. And this is kind of a summary of that spectroscopy. This is a plot that I recoiled from when Ida first showed it to me, but I've learned to love it. What we've done is we've subtracted off the vibrational bandhead energy from everything, and then grouped them. This is the lowest rotational state, L equal 1, L equal 2, L equal 3. So the different rotational states are there. And within each of these groupings, then, it's the vibrational variation of that. So the lowest ones that you see here, the green dots are the experiment, and the red crosses are Ida's theoretical calculations. And so these mark the V equal 8 lines that we see up through V equal 14. And so you can see rotational structure, you can see hyperfine structure, and we've learned to call this Hund's case B beta F3. So if you go to Frosch and Foley, you'll find out how to do all of that. And if we take out the rotational energies as well, what you see then is that in some of these groupings, so again, these are the different rotational states, and we've just spread out. What you see is hyperfine structure that's similar for the even rotational states and similar for the odd rotational states. And then within that, there's an additional splitting on some of these that you see with more lines, that these are spin-spin dipole splittings on top of the hyperfine interactions. And if we take our, of course, most favorable example of that and plot that for you, you can see that as you change the vibrational state and go deeper and deeper in the potential well, this spin-spin dipole splitting gets up to relatively large size, and we can study this variation with the different depth in the well. And so what we see is the spin-spin dipole effect is essentially you have electron-spin dipole interaction here. And it's essentially, it's a 1 over r cubed dipole-dipole interaction averaged over the vibrational motion. It's a relativistic effect, if you will. If you look at this, I don't swear that we have calibrated everything properly yet, so I wouldn't swear to the absolute locations of our experimental points just yet. But on this, the separations are pretty good. And you can see that in this plot, we've essentially matched the rightmost quantum state in this splitting. And if you then look at the leftmost, there's a significant discrepancy between the experimental splittings and the theoretical ones. And this we had to kind of go to the last, our biggest example here to get these to deviate from the theory. We really had to work hard to get deviations from the theory. But it's possible that this is second-order spin-orbit interaction, which has terms of the same form in there, and that's basically what we think we're seeing in there. And so with that, let me just summarize that while the optical Feshbach or Beutler-Fano resonances may or may not be useful for altering scattering lengths in Bose condensates and things like that, it provides an interesting and fruitful way to look at the whole photoassociation process. And I think this is something that we really owe to Ugo Fano's lessons, is that regardless of the math applies to so many physical situations that we can really get some different insights from combining our looking at all these different problems. And then closely related, these multicolored photoassociation experiments gives us an improved view of the interactions of alkali atoms by doing the spectroscopy of the dimers. Thank you.